Humanity is preparing to return to the moon, not for a flyby, not for a test, but a landing, the first in more than 50 years. This is Artemis III, a mission designed to land astronauts on the lunar surface and begin a new era of exploration. But behind the headlines, something isn't going as planned. Artemis III is the mission that changes everything. Unlike Artemis II, this one lands. Astronauts will travel to lunar orbit, transfer to a landing system, descend to the lunar surface. The landing site is unlike anything from Apollo. Artemis III targets the moon's south polar region, a place with permanent shadows, extreme cold, and potential water ice. Water ice changes everything. It can be used for drinking water, oxygen, rocket fuel, making long-term missions possible. Artemis III is not a simple mission. It requires multiple systems working together. Space Launch System, Orion, a lunar lander, all operating across deep space. Apollo missions were direct. Artemis is modular, more flexible, but also more complex. Artemis III has already been delayed. Originally planned earlier, now pushed toward the later part of the decade. Delays aren't just scheduling issues. They reveal deeper challenges: technology readiness, integration complexity, risk management. And one system in particular may determine whether this mission succeeds or fails. Because unlike any moon mission before, Artemis III depends on something that has never been proven in this way, a system still under development, and without it, the mission cannot happen. Artemis III is designed to land humans on the moon, but unlike Apollo, NASA isn't building the lander alone. Instead, they've chosen a completely different approach, one that depends on a system that has never completed this type of mission before. Artemis III, the lander system. For Artemis III, NASA selected a version of Starship developed by SpaceX, known as the Human Landing System. Why Starship? Starship offers something no previous lander could: massive cargo capacity, reusability, ability to support longer missions. It's not just a lander, it's a platform for future exploration. But there's a complication. Starship is still in development, and while test flights have shown progress, many critical capabilities are still being proven. The refueling challenge, one of the biggest technical hurdles: in-orbit refueling. To reach the moon, Starship must be refueled in space, not once, but multiple times. This requires multiple launches, precise docking in orbit, and transfer of cryogenic fuel, something never done at this scale before. Artemis III is a sequence of missions. Starship launches, tanker missions refuel it, Orion launches with crew, systems meet in lunar orbit. Every step must work. If one part fails, the entire mission can be delayed or canceled. Lunar orbit rendezvous. Once in lunar orbit, Orion and Starship must meet, docking in deep space far from Earth. Transfer to the lander. Astronauts will leave Orion and enter Starship, a completely different vehicle designed for descent. Descent to the moon. Starship will then begin its descent using powerful engines, navigating uneven terrain, aiming for the moon's south pole. Unknown landing conditions. The South Pole is not well explored. It includes shadowed craters, rough terrain, limited sunlight. Visibility challenges. Lighting conditions are extreme, long shadows, low angles, making navigation difficult. Why this is different from Apollo. Apollo missions landed in relatively flat, well-lit areas. Artemis III aims for a far more challenging environment. Technology dependence. The mission relies heavily on autonomous systems, advanced sensors, real-time decision-making. What's at stake? If Starship performs as planned, Artemis III succeeds. If not, the entire mission timeline shifts. Everything about Artemis III depends on this system, not just landing, but reaching the moon at all. And even if Starship works, even if every system performs perfectly, there's still another challenge waiting: the moon itself, a place far more hostile than most people realize. Getting to the moon is only part of the challenge, because landing on it is something entirely different, especially in a place humans have never explored before. After traveling across deep space, the crew aboard Artemis III prepares for descent. The destination? The moon's south pole. Unlike the Apollo missions, this region is extreme. It includes permanently shadowed craters, uneven terrain, and unpredictable lighting. Some areas of the South Pole have never seen sunlight. Temperatures there can drop below -200 degrees Celsius, cold enough to freeze equipment and make operations extremely difficult. Other areas receive near constant sunlight, creating blinding brightness and deep shadows, making depth perception difficult. As Starship descends, it must avoid hazards, identify a safe landing zone, and adjust in real time. Lunar dust becomes a major issue, fine, abrasive, and easily disturbed. During landing, engines kick up massive clouds of dust, reducing visibility to near zero. Lunar dust can damage equipment, interfere with seals, and affect visibility. It's one of the biggest unknown risks. Finally, the lander reaches the surface, a controlled descent in one of the most difficult environments ever attempted. The hatch opens, and for the first time in decades, humans step onto the moon again. This is not the moon of Apollo. The terrain is harsher, the conditions are more extreme, the risks are higher. The crew begins their mission, collecting samples, analyzing terrain, searching for water ice. Water ice is the key objective. Found in shadowed regions, it could support future missions. Astronauts cannot stay indefinitely. Exposure to radiation, temperature extremes, and equipment limitations restricts how long they can remain. Every movement must be planned, every step must be careful, because there is no rescue, no quick evacuation, and no margin for error. The crew is far from Earth, alone on the surface, dependent on their systems. The reality of the moon. The moon is silent, empty, and unforgiving, a place where survival depends entirely on preparation. And while the mission on the surface is critical, it's only temporary, because eventually they have to leave. And leaving the moon may be just as dangerous as landing on it, because everything depends on one moment, liftoff, from a surface where nothing can go wrong or there's no way home.
The mission on the surface is complete, samples collected, data recorded, objectives achieved, but none of it matters if the crew can't leave the moon. Inside the lunar lander, a version of Starship, the astronauts prepare for ascent. Systems are checked again, fuel levels verified, navigation locked in. Unlike Earth launches, there is no backup rocket, no rescue mission, no margin for delay. If ascent fails, the crew cannot return. Everything depends on engine ignition, structural integrity, precise guidance, all functioning perfectly. Engines ignite, dust erupts from the surface, the lander begins to rise, slowly at first, then accelerating into the black sky. The spacecraft climbs away from the moon, leaving behind the landing site, the equipment, the surface they just explored. The goal is precise: rendezvous with Orion in lunar orbit, a moving target traveling thousands of kilometers per hour. Even small errors in trajectory could prevent docking, and without docking, there is no way home. Much of this process relies on automated guidance, onboard navigation systems, limited real-time correction from Earth. Signals between Earth and spacecraft take time. The crew must act independently, making critical decisions in real time. As the lander nears Orion, relative speed must be reduced, carefully, precisely. Docking is one of the most delicate operations in spaceflight. Two spacecraft, moving at high speed, must align perfectly. Risks include misalignment, system malfunction, loss of control. Any of these could compromise the mission. Finally, the docking mechanism engages, the spacecraft connect, the crew transfers back into Orion. The lunar lander is no longer needed. The crew returns to Orion, preparing for the journey home. At this point, the mission has achieved its most difficult objectives: landing, surface operations, safe ascent, successful rendezvous. But one phase still remains: the return to Earth, a journey that will push the spacecraft and the crew to their limits. Because coming back from the moon means surviving re-entry once again at extreme speeds, under extreme heat, with no room for error. And after everything they've already endured, this final phase may be the most dangerous of all.
The moon is behind them. The landing is complete. The mission objectives achieved. The crew is back aboard Orion. But one final challenge remains: getting home. The journey back. The crew aboard Artemis III begins its return to Earth, a journey lasting several days across deep space. Leaving lunar orbit, Orion performs a burn, escaping the moon's gravity, setting a course back toward Earth. System monitoring. Every system is checked continuously: life support, navigation, thermal control. After everything they've experienced, nothing can be taken for granted. Cumulative stress. The spacecraft has endured launch forces, deep space exposure, lunar operations. Now it must survive one final test: Earth approach. Earth begins to grow in the distance, a familiar sight, but one that signals the most dangerous phase ahead. Extreme re-entry speed. Returning from the moon means re-entering Earth's atmosphere at nearly 40,000 kilometers per hour, faster than low Earth orbit missions. Atmospheric entry. As Orion hits the upper atmosphere, friction builds instantly. Temperatures rise dramatically. Plasma formation. The capsule becomes surrounded by plasma, a glowing shell of superheated gas, blocking communication once again. Final blackout. For several minutes, mission control hears nothing: no data, no voice, no confirmation. Waiting on Earth. Engineers and controllers can only wait, hoping the spacecraft emerges from the blackout. Heat shield performance. Orion's heat shield faces temperatures of up to 2,700 degrees Celsius, protecting the crew from extreme heat. Precision matters. The entry angle must be exact. Too steep, and the capsule burns. Too shallow, and it skips off the atmosphere. Deceleration. As Orion slows, the forces on the crew increases, pressing them into their seats, testing endurance. Parachute deployment. Once through the most intense phase, parachutes deploy, slowing the spacecraft for landing. Splashdown. Orion lands in the ocean, ending one of the most complex missions ever attempted. Crew recovery. Recovery teams move in. The hatch opens. The astronauts emerge after completing humanity's return to the moon. What Artemis III changes. This mission is more than a success. It's a transformation, proving that humans can land on the moon again, operate in extreme environments, return safely. The next step. Artemis III is not the end. It's the beginning of lunar bases, long-term missions, preparation for Mars. A new era. For the first time in decades, humanity is no longer limited to Earth orbit. Deep space is open again. Everything that comes next depends on this moment. Beyond the moon, beyond the missions we've already imagined, lies a future where humans live beyond Earth. And Artemis III may be the step that made it possible. The question is no longer whether we can return to the moon. The question is how far we're willing to go next. Subscribe to Obscura Cosmos for deep space mysteries, real mission breakdowns, and the future of human exploration, because the next mission could take us even farther.